Okay, so we'll start today with moving into sort of really the first functional group, hydrocarbons, so alkenes and alkynes. We're going to focus primarily on sort of alkenes to get things going. So we'll do kind of the boring stuff, nomenclature. I'll tell you the rules. Nowadays, you just plug a structure into a program, it names it for you. So we'll look at some basic things to get an idea of how the algorithm for naming has been developed. And then the important stuff is later on when we start talking about conformational analysis. And so we're going to look at a model here, which is the bigger version of what you have for your lab class. I would strongly encourage you to start using those models as you go through these problems, because you want to be able to visualize these things in 3 dimensions. And so what we do now is going to translate into reactivity as we move into the modules 4 and 5 of this semester. So the reagents that we learn not only carry out transformations, but they do it in a very specific way. And so the models show you kind of a representation of the bonds, but we still need to know things about sort of angles and how electrons move to specific carbons and hydrogens. So to start it off, the kind of evolution of what you're going to see for the remaining part of the semester here is we're starting with hydrocarbons because they are isolated from natural sources, and after reactions are applied to them, they make new compounds with different properties, and that's what we as humans use in civilization. So for example, the Nobel Prize in Chemistry was awarded this morning. Does anyone know what for? So MOFs, metal organic frameworks. So those are compounds that have been studied, and one of the applications is they can kind of store gases. So if you have a MOF and you can store hydrogen gas in it, then you can run cars on hydrogen gas instead of gasoline. So as I show here with the slide, There Will Be Blood. Show of hands, who's seen that movie? Am I the only cultured person in this class? If you have Netflix or Hulu, whatever, I suggest watching that. It's based on a book called Oil by Upton Sinclair, and it's really about kind of what it is to be an American, in the sense that Daniel Day-Lewis is trying to get rich and famous, and the means by which he's doing that is prospecting for oil. And so, as we know, petroleum produces gasoline, but there's other things in it. So these constituents, which are hydrocarbons, so just CC and CH bonds. And then from that, we're going to learn how to apply reactions to make more complex molecules. And those reactions occur through different mechanisms. But now what we want to sort of review are the 3 main hydrocarbon functional groups. We have alkanes, alkenes, and alkynes. So we're going to use different terms as applied to these. So alkanes are saturated. And when I use that term, you should think of sp3 hybridized carbon atoms that have 4 sigma bonds. And alkenes and alkynes are unsaturated. So you have sp2 and sp hybridized carbons. And the way that an organic chemist thinks of unsaturation is there's opportunity to form new bonds. And that's primarily module 5. So this module is setting the stage for module 4, which is reactions at sp3 hybridized carbons. So don't forget this CnH2n plus 2. We invoke that to determine degrees of unsaturation. And we're going to start with, some of the nomenclature rules, just so you get an idea of that. It's not terribly exciting, but these hydrocarbons do come from petroleum primarily. There are other sources such as plants. So if you've heard of like biofuels, plants can produce oils as well. But petroleum is really the main source from which a lot of economies run. So the rules for nomenclature, I would say based on the carbon count, for lack of a better word, you want to memorize the names of carbons 1 through 10. Anything beyond that, we're really not going to focus too much on. But what you see in the 3 functional group columns, I have the A, the E, and the Y underlined. And so in the parent name, that ending or suffix will change, and that's telling you what functional group is present. So for alkanes, you'll notice that they all end in ane. And then once we get past 4, the front part of the name takes on that prefix that we can determine a number from. So methane, ethane, propane, and butane, that first part doesn't really tell you the number of carbons, but everything after 5 and above will. So for pentane, pent, we think 5, and then ane is an alkane. And as we add unsaturation in terms of pi bonds, we get to alkenes. So notice the front part of the name stays the same. So eth, and then we just change that to E. So ethene is telling you that it's an alkene. And then for alkynes, we use the Y. So the first rule of nomenclature really is what is the parent carbon chain? How long is the longest linear chain in a molecule? So you do a carbon count, and then you're going to come up with one of these parent names. And then from that chain, you have stuff hanging off it. Those are called substituents. So we have to find what carbon those substituents are bonded to, and then what are they? Are they other carbon chains? Are they heteroatoms? So the nomenclature will always have substituents and then a parent. There's a little bit more nuance to it, but it's pretty logical for the most part. These are some of the rules. If you want to really put yourself to sleep other than this lecture, you can go to the IUPAC website and look up the nomenclature rules. It's basically just an algorithm of, if you're given a structure, how are you going to name it? Just to not reread everything on this slide, but to give you an idea, you have a molecule with a carbon chain. You count the pathway of the longest carbon. So whenever there's branching, you can get these different pathways. So you have to take the longest pathway. That's going to give you a carbon count that corresponds to the parent name. Anything bonded to that is a substituent, and you have to put a number in front of the name of the substituent. The numbering can get a little ambiguous, so we'll go through an example or two of that, of what's the right way, what's the wrong way. But the main thing after finding the parent is the substituents are listed in alphabetical order. So they're not listed according to the number they're located. It's alphabetical order. And then if there's two of the same thing, we'll get into that nuance as well with kind of other prefixes. So when I say alkane, I'm referring to the linear chain. If you have a substituent that is a carbon-based group, the alkane nomenclature changes to alkyl. So you fire the A and E, and then you replace it with YL. And again, that's based on the total carbon count. So we'll look through some examples of this, and that comes into play when there's branching off the longest chain. The other functional groups that you learned, things with heteroatoms, so like OH hydroxy group, that's alcohol nomenclature, and then that'll be slowly introduced as we learn those different functional groups. But for now, we're mainly looking at just stuff with carbon and hydrogen. In addition to identifying longest chains and substituents, we also want to start classifying things in terms of, a carbon, how many other carbons are bonded to it? On a carbon, how many hydrogens are bonded to it? So we use these, draw a line right here. Yeah, maybe I'll draw that line. So primary, secondary, tertiary, and quaternary. So those are the words. Those words can be represented as numbers with that little degree sign. So for example, a primary carbon is bonded to one other carbon. So primary hydrogens are bonded to primary carbons, and we would call that a methyl group, so CH3. So secondary, the carbon's bonded to two other ones. For hydrogens, we describe that as methylene, or CH2. Tertiary, 3 carbons, that ends up being a CH or methine group. A carbon with 4 non-hydrogen things bonded to it is called quaternary. And notice you can't have a quaternary hydrogen. So that's just C. There's no H's attached to it. The reason that knowing this is important, when we learn our first reaction of CH substitution, you have to classify every carbon and every hydrogen in a molecule according to that pattern there. And then depending on the reagents you use, you can rationally predict where a hydrogen is going to get substituted. There's a kind of a thermodynamic argument for why of 3 unique sets in a molecule, only one of them will react. Why don't they all react? So being able to do that is pretty important to predicting what the major product of a reaction is. So let's just start drawing some stuff, and I'll point out these rules. The stuff I'm going to draw is all captured on the next slide, but we'll go through it. We're going to start with C4, C5, and C6. Because for those carbon counts, you can have linear and branched isomers. And then when you get into the branched ones, that's when the nomenclature rules apply. So for 4 carbons, that's saturated, we can have C4H10. And so from that, let's draw out the possible constitutional isomers. So maybe I want to put, can I move this? No, I can't. Can I erase it? No, I can't. All right, I just want to put another kind of thing up here, linear. And then over here, branched. So for a linear compound, you're just drawing the longest chain possible. So four carbons in the longest chain. And so that was butane. If we start classifying things, so above each carbon, I'll write what type it is. So we have primary, secondary, and primary. So when you determine like the uniqueness of the carbons or hydrogens, the next thing you can do is classify what each type is. So if we wanted to draw a branched isomer of C4, that means we have to go down in carbon count of the longest chain. So this would be now starting at C3. And so we know a 3 carbon count molecule is called a propane. But now we have that other methyl or carbon group we have to put in there. So in red numbering, I'm just numbering the chain 1, 2, 3, so that's propane. But we have that 4th carbon. We can't put it at 1 or 3 because that just makes the longest chain. So we have to put the last one at position 2. So what I circled in green, that's the longest chain. And then I have this thing hanging outside the circle of trust here. So it's 1 carbon atom. So 1 carbon is methane, but because it's a substituent, it's now methyl, and it's at the 2 position. So that would be 2-methyl propane.
Can you say that again?
So that it's 1 carbon. So 1 carbon's methane, so it becomes methyl when it's a substituent. It's at position 2. And then we would say 2-methyl propane. So in blue, I'll write the classifications. So primary, 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 and then this one is tertiary. So we'll do the same sort of activity for C5 now. There's only ever one linear isomer for each carbon count. Everything after that has to be branched. So there's pentane. We have primary, secondary, 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 and primary. So for the C5, when we go to the branched, now we have to start with a butane derivative. So butane is the longest chain. It's now the parent. The last carbon is going to be a methyl group. So the logic of this, you can never put it at the end. It has to be an internal carbon. So this would be 2-methyl butane. So a common sort of question is, can it be 3-methyl butane? So the answer for that is no, because once you determine the longest chain, the substituents have to get the lowest possible position they can. So when I drew it this way, I see how I numbered the chain like that. So really, when you get into these more complex ones, you'll find that you can number the chain either left to right or right to left. And you should probably practice doing both ways to determine what the name is so that you see the outcome where the substituents get the lowest possible number. So the next isomer that we're going to draw is going to show that. So we can draw another branched C5 isomer. We can't do it as a butane derivative because that's really the only thing we can do with that. So we can shorten the chain one more down to 3 carbons. So that's now propane. Now we have 2 carbons to deal with. Neither of them can go at 1 or 3, so both of them have to go at position 2. So the longest chain is propane. At position 2, there's 2 methyls. You have to specify the position of both, and then because they're the same, you have to put a prefix in front of the methyl. So this will become 2, 2, the dash, and now that di, because there's 2. So 2, 2 dash dimethylpropane.
And the first 2 just shows that it's also on the 2?
Yeah, so these 2 numbers here correspond to the position of the methyl. The di is kind of reinforcing that, that there's those. It just so happens they're on the same carbon, but let me go back in blue to point out the classifications of the top one. So primary, tertiary, secondary, primary. And then for the propane derivative, all the methyl groups are primary. And now we see the first case of a quaternary carbon. So a carbon with no hydrogens bonded to it. So as I said, it's not the most exciting thing in the world. But if you understand the logic, it's pretty straightforward. The other way to think about this, if you're given a name, how do you convert a name into a structure? So even though we're taught to read, left to right, when you're converting a name into a structure, really you want to look for the parent first. What's the longest chain? Draw that out. Number it. And then look to the front of it. What are the substituents? So the substituents will always have a number that's corresponding to where they are on that chain. The other thing is, so far we've only seen kind of one unique substituent. Whatever those groups are, they're listed in alphabetical order. They are not listed according to number. So we'll see some of that in the examples coming up. In essence of time, so I can kind of get through stuff, I'll just talk through the C6 isomers on this slide. So here you see the C4, the C5, the C6. There's the linear isomer, so hexane. And then when you're doing the branched ones, for any N carbon, there's only one linear. And then if you want to be, approach this in a rational manner, you do N-1, then N-2, N-3, N-4. That will help you really to prevent redrawing something you did before. So for the C6, the N-1, these are going to be pentane derivatives. So we have 2-methylpentane, and then we can draw another one where the methyl group is at the 3 position. And so you could probably practice on these, classifying them according to primary, secondary, and tertiary. Yep.
Why can't we put it on the 3 this time, but not during the 10?
So for this one above here, the reason you can't put it there is really because you're just redrawing this molecule. So those are the same thing, and kind of what we're going to get to later today. All they are is it's just a rotation. If you rotate one, you can map it on the other one directly. From the pentane derivatives, we can now go down 2 to the butane derivatives. And so when we do that, those 2 carbons, we can either attach them to the same position, so 2,2-dimethylbutane, or then carbons 2 and 3 each get their own. So notice now it's 2,3-dimethyl. So even though they're methyls, we're differentiating their location based on that number. Let me just point something out real quick. So I like this molecule a lot because it has the relevant classes we need: primary, secondary, and tertiary, so it has one of each. The first reaction that we're going to learn is a CH substitution. So a hydrogen is going to be substituted for a halogen. When you look at this molecule, we have so 4 unique sets of hydrogen. So 6, 3, 2, and 1. So those are the unique sets, those are the ratios, and then these would be the classifications of those ratios. The goal of any reaction is to produce one thing in 100% yield. When we look at these 12 total hydrogens, we've narrowed them down into these different classes. How do we know where a substitution is going to occur? There's 4 possibilities. We could substitute something here, something there, or there. And we don't want it to be like, oh, whatever, it's random. There's, known from the chemical research in the literature, there's like a known algorithm of exactly what hydrogen is going to get substituted. So when you look at a starting material, you look at the reagents, you can say the major product is going to be substituted at this specific hydrogen. So it's not random, and I don't want you to feel lost like it is random. So going through this classification process is going to help you understand what is going to be produced from a reaction. So if you want to practice nomenclature, what you can do, start with the C7, H16 count. The first one's heptane, but then look at, the N1, N2, N3. There's 9 total isomers. If you're really bored, you can go up to the C8. There's 18 total isomers. So if you draw them out, that gives you practice applying the nomenclature rules. And then as we increase, you can see that it starts going up quite a bit. And so that is called enumeration of alkanes. And again, once you see the patterns of how to do it, it's pretty logical. But the tough thing about it is you don't want to redraw something you already drew. So I'm going to grab some water. Why don't you look at that? It almost looks like a crack in the screen, but it's actual molecule. See if you can figure out the name of that. So maybe a crappy analogy of this is like those drawing books. So I have a son in kindergarten, and there's these books with like mazes. How do you get to the end? You can kind of think of this as a maze where like a terminal carbon is your entry point. So you enter, you follow a path, and then you exit. So you can count that as one path. Then sort of go through these different paths. See how you can find the longest carbon chain. That's then your parent. So how many carbons are in the longest chain? So there's 9, so it's going to be a nonane derivative. So we can eliminate the octane and hexane. And then we're left with A and B. The other nuance between A and B is you have to maximize the number of substituents possible. So there's a flaw with one of them where you're kind of lumping too many carbons together in one of the substituents. So what do you think the answer is? I heard some B's, I heard some A's. My recollection is it's A. So to my prior point, I think that is the issue right there. There's too many carbon atoms in that substituent, and it has to be expanded out further. So let's, based on that being the correct answer, let me just put the numbers on the chain. So you can number the chain again two ways, the right way and the wrong way. The way you determine what's right is that the substituents have to get the lowest possible numbers they can. So let me point out, we have the longest chain is 9, so that's the nonane, and then everything in front is the substituents. Now here we have 3 unique substituents: ethyl, methyl, and propyl. So they're listed in alphabetical order. Then the number before it is where they are on the chain. So there's your 9. There's your ethyl. Here's your dimethyl. I want green. And then there's your propyl. So let me point out so what does that equal? 15? So the way you ultimately test it is you take those positions, you add them, and they should give you the lowest sum. If you number it the other way and you get a larger number, that's the incorrect way. Any questions? Yeah.
How do you know that it does that 9 and not the other 9 molecule?
So I'll try to do this in a different color here. So that would be the other way of doing it. So the ethyl would be at 4. Then we would have the dimethyl at 5 and 7. And then the propyl at 6. So that would give you, is that 22? So
How do you know that it's the one at the top to the 9 on the left instead of the 1 on the propyl to the
instead of it's like starting here.
Yes.
Yeah, so that would give you B. So the what's wrong with B is that it's lumping all of this stuff into there. And that can be further broken down into more substituents. So there's a kind of way of looking at the different paths, and the green one is the right path. As I just said, with B that's in yellow, that's the incorrect path because you're getting into, you have a substituent, but that substituent itself is then branched. So you want to minimize that when you're applying these rules. And then C and D, the path length is too short. So which one of these is 4-ethyl 2,3-dimethyl octane? Any guesses? So B. So again, alphabetical order for the substituents. This di, you don't count that for alphabetical. It's the substituent itself. So that little prefix there. We would not say 2,3-dimethyl 4-ethyl. So it's the M and not the D. I'll let you practice this one on your own. It's kind of more of the same. So I want to get into this issue now where if you do have a substituent and that substituent is branched, there are these common names that apply to these different scenarios. So what you see here are some patterns of branching of a side chain or a substituent. So iso means same. Isopropyl is when you have 3 carbons and it's attached to the second one. Isobutyl, so butane is 4, isobutyl now. You have kind of this propane chain, and then the 4th is coming off. So that's the iso there is relates to the methyls. Sec means secondary. So you have a chain that's branching at the secondary position. T means tertiary. So tertiary butyl. Now the point of attachment is that quaternary carbon. So tert butyl is a quaternary carbon plus 3 methyls. And then neo, I'm not sure if that's short for anything, but neopentyl, there's 5. You have basically a tert butyl and then a methylene linker. When these are part of the substituents, you don't consider that prefix as part of the alphabetical order. So here are some more examples where now we're finding the longest chain, but the substituent has a branching point. So we'll go through one of these to determine the name, and then there's a couple more examples you can do on your own as practice. So with this one in particular, what is the IUPAC name? Any guesses? So B would be the best answer. So 7 gets us the heptane. And then when we look at the substituents at the 3 position, there's your ethyl. And then at the 4 position is that tert-butyl. So again, notice that we don't consider the T as part of the alphabetical requirement. It's the B. So B is before the E. Again, notice that in terms of that ordering, these numbers they don't play a factor. So I guess what is wrong with choice A? Why is A not correct? So it numbers the chain going the other way. So if you take 4 plus 3, that's 7. When you do it the other way, you get 9. And as part of the rules, they have to get the lowest possible numbers. C is incorrect because the alphabetical order is reversed. And then I don't even know what would be wrong with D, because you wouldn't arrive at like that structure if you translated it back. So here are some ones. Well, I guess they're listed for you, but you can look at the name and make sure that you understand how the name translates back into the structure. So let me see where we're at here. Since we're talking about alkanes, we'll lump in cycloalkanes with that. And really what you're doing is just finding the largest ring size and putting the word prefix cyclo in front of it. So we need a minimum of 3 atoms for a ring. So cyclopropane, cyclobutane, then you just go up. And for any N carbon count, you only have one of the largest rings, and then you can do the same exercise where you decrease the ring size, add the remaining carbons back in as substituents. And you'll notice I didn't fill this table in because when you start getting up to here, it generates quite a bit of isomers. And then another thing that happens that's related to this module is a concept called stereochemistry. So not only do you get constitutional isomers, but then you can get these other type of isomers that will increase that total count even more. And one last nomenclature thing with cyclic compounds, because we'll study some selected cases of these as we move forward. There are bicyclic and then spirocyclic compounds. So bi means two. Spiro means there are two rings connected by a quaternary carbon. So let's look at this smallest one here. I'm not just hallucinating and making up weird geometrical shapes and ChemDraw. These things actually exist, and they're used as reagents for synthesis. But let's see if we can make sense of the nomenclature. So bicyclic compounds always start with bicyclo. The parent is the total number of carbons. But what do you think this stuff in the square brackets mean? So where they're joined, where they're connected. So let me highlight where these two rings are joined. I'm going to highlight that in red. And I'm going to call that a bridge. So you can start from the top, walk across that bridge, get to the other side. That bridge corresponds to this number here, 0. Because you're not encountering any carbons when you walk over that. So maybe in blue, if we go this way, we've walked over 1 carbon. Then the other way, we've walked over 1. So with bicyclic compounds, there's always these 3 numbers reported. And then you can kind of see the logic of the other ones as well. I'll highlight. So I'll do. So this bridge, we have 2. That one we have 1. And then that one we have 1. So it's just reporting the number of carbon atoms that you encounter from walking from one point of attachment to the other where the 2 rings are joined.
And it always goes from highest number to lowest number?
Yeah. So notice with spirocyclic compounds, there's only 2 numbers reported. That's because they're joined only at that 1 carbon. And so really what you're doing is just counting how many carbons are in each ring. So 2 and 2, that's what you would report there. So the other one has 2 and then 3. Yeah. I guess, so for the bicyclic ones, yeah, I think they're always like highest to lowest. For these, I don't know if that's my mistake or if it's then increasing for these. I'll have to check on that. Any questions before we move on to the next concept? So that's nomenclature again. There's just the best way to learn it is to practice it by drawing out the different branched isomers, finding the chains, the substituents, and you know, figuring out what's right, and if things are wrong, why are they wrong? So this next thing, conformational analysis, really relates to the fact that molecules always have energy. So the energy means they're doing something dynamic. We saw that with infrared, where there's stretching of bonds. So you have two atoms, they're stretching because of that potential energy curve. Conformational analysis really now relates to another way of moving, specifically rotation. So instead of stretching, now we're rotating. From the most basic standpoint of this, we're only going to first consider this with two atoms in a sigma bond. So we know that due to the orbital overlap, sigma bonds can rotate. Pi bonds, because of that double bond, cannot freely rotate unless that double bond is broken first. So the conformational analysis really just relates now to sigma bond rotation. So because the Nobel Prize in Chemistry was awarded today, this topic was actually recognized with a Nobel Prize in 1969 to Derek Barton and Odd Hossel, who really started to describe that, when you draw these things on paper, you're drawing like a snapshot in time, but in reality, these things are always moving. And as part of that, when you draw something static, it's kind of one picture. You draw it another way, it's another one. So in a sense, the way you draw things are isomers. So conformational isomers or conformers. And we'll see that as we analyze conformers through sigma bond rotation, the population of those conformers is not always the same because you have different interactions that can happen. So at any temperature, a molecule can sit one way. If you put energy into it, maybe another conformer is preferred. So that the learning tool to do this is the Newman projection, which we saw when we were analyzing the magnitude of a coupling constant in proton NMR. And so now we're looking down a carbon-carbon bond axis. And so the front carbon is represented, kind of by this, in this sense, this inverted Y. As we look down that axis, the circle is the back carbon, and then the lines coming out of that are its substituents. So when you overlap this on top of that, that's the Newman projection. So that thing right there is your front carbon. The circle is your back carbon. So you have to be cognizant that the front to back is a sigma bond. And then you have 1, 2, 3 substituents on the front, 1, 2, 3 on the back. So we'll run through here's red up and blue down. So here's ethane. So 2 carbons. The yellow ones are hydrogen, but the red and the blue purple one, that's hydrogen as well. And I'm using the different colors so that you can see that something actually is happening. So normally, when we draw structures that are in the plane of the board, you always draw like the longest chain in the plane. So you're looking at the molecule, kind of 90 degrees to this sigma bond. And what the Newman projection is just rotating it. So your frame of view is different. And that's the projection. So I've taken this left one, and now all I'm doing is turning it this way so that the red one is at the top and this blue one's at the bottom. And so again, that sigma bond, you don't see it because it's in line of the projection. And so what are we doing? I'm keeping the back. When you do this, you want to keep something stationary. You can't move 2 things at once, so you need a reference. So I'm keeping the blue one, if you notice, down for every rotation. So when you look down that, all of the substituents are staggered. And then if we rotate, it's subtle, but now they're eclipsed. So staggered, eclipsed. And because it's a sigma bond, they rotate. So in general, a staggered conformer is more stable than something that's eclipsed. So the models are, again, not the best thing in the world to understand this because a bond isn't a stick and an atom isn't a ball. Remember, these things take up space. So when this rotates, looking at it this way, these things want to move away from each other. So when they're eclipsed, there's an energy penalty for that. That's, you can think of it a couple different ways, like strain. You have to put energy to get past that eclipsing. And so it says for each hydrogen eclipsing, it's plus 4 kilojoules per mole. So we have 1, 2, 3 sets of those. So total, that's 12 kilojoules per mole. To get past that over to this. Because everything is hydrogen, all those eclipsing are the same. So what we're going to do is, okay, ethane is pretty simple. We'll plot what that looks like. But what happens when you change one of these red or blue ones out? You start making carbons. Now you have different eclipsing interactions that are higher energy penalties. And so you'll see that from staggered versus eclipse. Notice the red and blue So what's the dihedral angle now between red and blue? 180. So 180 and then 0. So you're going to have these different conformers, and this is probably the most stable one, right? But that one's not because the penalty's higher. And that sort of subtle difference can translate into how different products react. So maybe this reacts faster than that. And so as these things rotate, we have to consider how does it affect the reactivity. So that energy penalty enlisted in the menu here were HH. So there were 3 of them. So the eclipsing interaction has a penalty of 12 kilojoules per mole. And really what that means is this conformer of staggered is more stable, it's lower energy. When you get to here, it's now higher energy. So low, you do this. This is now higher energy. It doesn't want to exist like that because there's a penalty involved. So here's an empty slide you can duplicate and sort of do these things with, but what we're doing is looking at the dihedral angle between 2 substituents and considering when things are staggered, then they go to eclipsed, what is happening, what penalty is there, and then we plot it versus energy on the y-axis. So for ethane, this is the kind of curve that results. We're keeping that blue hydrogen the same and then rotating the front red one clockwise. So the staggered we're saying has, and this is relative energy. I don't mean there's no energy, but relative to the staggered one, when you do the eclipsed, it's plus 12 kilojoules per mole penalty to get past that rotation. As it goes down through another rotation, it's staggered again, so it goes down to 0. And then this just repeats because all of those things are the same. But as you start putting different substituents for the red and the blue positions, you're not going to get something that looks this pretty because the eclipsing interactions are different. It's going to relate back to one of these. And so for each one, you figure out what it is and just add those 3 numbers and then just plot it.
And before you multiplied 4 times 3 because there are 3 atoms.
Yeah, so when it's eclipsed, you have to look at each situation. And we're about out of time, but where we'll pick up with is looking at these next 3. The other thing I just want to mention briefly, since ethane only has 2 carbons, you can only look down 1 sigma bond. But as you start adding more carbons, you have to specify what carbon in front and back, because if red and blue are different, then your perspective of looking down at your